Hi, I'm Mohamed Gowely. I'm a fourth year undergraduate mechanical engineering student here at Queen Mary University of London. In this video I'll show you kind of illustration of how to use my notes. Well, certainly I'm not an expert of using any of the CFD packages, but that's part of the demonstration. Here's someone who's not an expert who can follow a general CFD method in running turbulence modeling approach around benchmark cases such as the Ahmed body. Please excuse my pronunciation, my English is not perfect, as it's not my first language because I'm an Egyptian. Let me first minimize this window so that I can share my notes with you. So here we go, that's the title page. Then some information if you want to reference these notes in any of your work. Later on, if you like the way this document is designed, I didn't create this template myself, but rather Matthias and Val did. Here's the link, you can download it too. Then acknowledgement, at the bottom of the page, the aims of the notes. Then this page gives you a brief idea of the tasks discussed and how the commands are represented. So when you see two vertical lines like this and blue text in this font, then definitely it's a command or a code. Then table of contents, the list of tables, list of figures, and the general CFD method flowchart. The first chapter is about the Ahmed body. We are looking at the Ahmed body. It's a simplified ideal car shown, surrounded by my own CFD streamlines, which was generated in ParaView. The aim of the first subsection, geometry, is to show you how to export any CAD file to ASCII as the encoding language and STL as the file format, which are the most suitable format for importing any CAD file into OpenFOAM. And by the way, I shared my own way in drawing the Ahmed model in Creo. I used Creo because I'm sure we got its license in Queen Mary's computer lab. You are free to use any of the CAD packages available and to follow your own way in sketching. Another thing, to follow the instruction easily, you can print it out and tick every step as you master it. Or if you prefer using an e-copy, then if you clicked on the number of the figure here, this will take you to the figure, and if you want to go back to the list of steps, just click this number, it will go back. As simple as that. Then second subsection, is about OpenFOAM. I presented the structure file, followed by the mesh generation subsection, starting by creating the virtual wind tunnel. Then I share the problems I faced when sketching the wind tunnel, but of course there are other ways to solve these problems. I just tried my own way and left the other way as an exercise. Nevertheless, I dropped you a hint. You will need to understand the general block topology of the block mesh utility in order to create the wind tunnel. So most of the block mesh dictionaries will look similar to this one. First, the default units of most of the CAD packages is millimeter. So either you convert it to meters by replacing the 1 by 0.001, or you do this in the terminal as shown previously in the first subsection. Then you define the coordinates of the vertex. Then it's important for this line to be in the same order as the way the coordinates of the vertices were defined here. So here I started by 0, I should write 0 here, and 1, and so on and so forth. Here I had to define the number of blocks in the X, Y, and Z direction. Then the Then the spacing, then I've chosen uniform spacing, that's why it's 1 in all directions. Then I had to define a name for the patches. So if that's the inlet, it's gonna be 0473, and the outlet gonna be 1265, and so on, which you will need when you define the initial conditions. The next thing is the Mohamed body. I just illustrated by a single flow diagram an overview of the mesh generation functionality in OpenFOAM. Snappy Hex Mesh has 3 processes. First is the castellated, second is snapping the mesh to the surface, and the third one is the layers addition, and a brief description about each. Then I shared the meshing strategy. So if you are testing any turbulence modeling approach around any of the benchmark cases, you can go through the literature and study the flow physics over the specific case, then start the meshing. Here is my mesh after so many attempts, which I'll present in a bit. Similarly, I shared the problems I faced and its solutions. And that's the meshing journey before I arrive at my final mesh. So presented here the case setup procedure, but first you have to solve these questions. You can easily print this paper to tick every step as you master it. Then I presented the setting the case in Helix, followed by setting it in the terminal manually. I'm still working on this part, the difference between OpenMPI and OpenMP. By the way, OpenFOAM supports MPI and not MP. Then steps on how to submit your parallel jobs onto Apocrypha. Here is a sample of the file script that you will need, which simply is a way of describing the set of processes that you want the SunGrid engine to run. I also shared my mistakes so that you can avoid them and save time and effort. Then the grid decomposition method. In order to run a parallel job, you will have to cut your computational domain so that it's distributed among the number of cores you're using. So this can be done and defined in the decompose par dictionary, which is available in the appendix. So OpenFOAM has 4 different strategies which are simplified in this chart. You can start your simulation by running a potential run. I included a link to a useful tutorial here, which will save you time and effort. Fourth, main subsection is how to monitor your job. OpenFOAM doesn't calculate the force coefficient automatically, or the residuals, nor the probes, so you have to do it manually by copying these lines into the bottom of the control dictionary file, which is located in the system folder. Also, if you want to plot the force coefficients on the go, I mean during the simulation, you can create a text document and copy the following lines, then type in this command, and similarly for the residuals and the probes. I included copy of the dictionaries and the plots in the appendix. And the 5th subsection is about paraview. You can visually check the cell aspect ratio and the Y plus in paraview by following these instructions. Then the post-processing subsection. So here is how you can adjust the camera view in order to have same views. Also steps in plotting the velocity contours, the velocity components, And here's my results for the transient detached eddy simulation results. So I wrote the steps in plotting surface vectors as checklist, similar for the glyph and the streamlines. Then the computational time for the simulation. Then the mesh refinement analysis, the regions where you need to refine and to coarsen the mesh, plotting the y plus so that you know where to coarsen the mesh to activate the Gowely function used. Here I plotted the contours. Another utility which isn't available in a regular OpenFOAM but rather in Foam Extend is the U residuals, where you plot the velocity residuals to check for errors in your mesh to be able to optimize the meshing criteria. I also tabulated the results to check how far is the mean value from the previous saved iteration. Last but not least is my results compared with the experimental ones obtained from Leanhard. And a set of useful links. Second chapter is about the Onera M6 wing. The geometry was created by the expert Matush Gugala, who shared the way he sketched it. Then the next subsection is about ISM CFD and generating the mesh in there. A more of a descriptive instruction on the meshing procedure. Then I shared the meshing journey with the mistakes written in black, while the correction method is written in blue between two curved brackets. Then followed by setting the case on Fluent. Then I still haven't completed all the notes because the license is being switched to another software called CD Adapco. Then here's the appendix, the SnappyX Mesh dictionaries, and followed by the time directory files, mesh decomposition dictionary, and the file script dictionary, file script text file, and the force coefficient graphs plotted by GNU plots for my simulations, then the bibliography and an index. So please email me if I made any mistakes in the notes, and thank you very much for listening.